Thank you very much for Christos for the wonderful introduction and for all of you for showing up. And I hope I will have something somewhat interesting to offer to many of you, though I'm a little afraid that many of you actually know some of the things I have to say. I guess I want to add one more thing to Christos' introduction. I was here on sabbatical.
I'm not Christos.
I'm so sorry to Dick's introduction. I'm so sorry. I want to add one more thing to Dick's introduction, is that I was here also, as Dick said, I was here as a postdoc and as one of my first postdocs and a first encounter with the US, but I also was here at 99-2000, and in fact it was influence of Berkeley interactions and in interaction with Christos that got me interested in game theory. And in fact, Tim was here as a graduate student, and I guess we have a lot to thank to Christos and generally the Berkeley environment to get us onto this interesting topic. So with this, I do want to talk about learning and efficiency in games. And I guess maybe efficiency will come in the second part of the talk. I want to start with learning in games. And I guess to get you set, I'm going to alternate between thinking of games where learning behavior from the players is a reasonable assumption, and I hope you will agree is a reasonable assumption, and thinking of very, very simple games where I can better illustrate of what exactly happens if people are learning. So I guess the kind of games I want to think of where I think learning is a reasonable behavior are any kind of game that happens over and over again. And I guess traffic writing is definitely one of them. If you're one of those car owners, and I don't know where the picture was taken, and you're driving in that car, chances are that this is some sort of morning rush hour traffic or afternoon rush hour traffic, and you're doing this every day. And in fact, really, you are learning. You're trying to figure out what is the best way to drive between the two notions you want to go. Similar things happening on the internet with packets, though it isn't exactly the packets that are learning, but instead the routers. But nonetheless, in some way, the same thing is happening. Someone is trying to figure out gradually what might be the right thing to do. Another domain of this form is advertisement, or certainly search advertisement, or any sort of internet advertisement where this model has been studied or considered. Again, if you're selling or buying ads in some search platform, and I guess it's a little fuzzy picture here of, I don't even know, I think Yahoo ads on the picture, then any particular ad here doesn't have much value, but yet this search advertisement is what supports much of the internet industry. And the way it does it, that there's millions of interactions here. And as a result, it's not at all a one-time played game. It's a game where you're bidding for advertisement that happens over and over again. I want to model this as a repeated interaction. And I want to think of the player's objective function as trying to minimize or maximize, depends what the objective function is. They want good average performance. They want to have good performance most of the time. This is definitely a good model for selling advertisement or buying advertisement. So I guess I want to think of games in which players interact over and over again in an environment. And I want to think of what should I expect to happen in this kind of games. Now, I said I'm going to think of learning, but I didn't tell you what I meant by learning, and that was not an accident, because the first part of the talk, I want to think about what I could mean by learning. What kind of models would I mean by learning? So I guess there are multiple models here of what one could consider, and maybe the simplest one is to assume that since they're repeating the same game, we can take the equilibrium of the first time period, assume they were smart enough, they figured out this equilibrium, and they repeat it over and over again. I'm going to call this the Nash equilibrium of the one-shot game. Or I could say that, no, that's not what they're doing. They're trying to influence the behavior of the neighbors, and I should think of something complicated, how I'm going to, aggressively do something in step 1 so as to intimidate the company so that in step 17 my life gets better. That would be the Nash equilibrium or the equilibrium of the repeated game. Instead of this, I want to say that they're engaging in a simple learning activity. And I'll come to try to give you options of what might mean by learning activity and also of how that relates to some of those other notions. Generally, by the end of the talk, I want to think about what can we, so in the beginning of the talk, I'm going to just talk about what do I mean by learning. Historically, how did games and learning interact with each other over in the beginning of this area. But by the second half of the talk, I want to talk about what can we say about outcomes of games. That is, what happens in a game if everyone is engaging in some sort of learning. And then hopefully, if I have enough time or a little bit at the end, I want to actually emphasize one particular advantage of learning compared to some of these other models of thinking about games, that learners are infamously or famously good to adjust for changing environments. If something changes in your environment and you're running a sort of learning algorithm, one would think learning is good at this. And certainly many forms of learning are good at this. And I guess I want to think about how does the game theory version of learning think about the fact that the environment might be changing as you're playing the game. Remember, this is a repeated game. If you're thinking of traffic patterns, maybe things change slowly in that business. Like it could be, somewhere a big company opens, a lot of people suddenly want to go there in the morning, or some road closes and therefore some other roads get more congested, so traffic patterns can change. And certainly in the internet advertisement business, it's even more prevalent. Something becomes popular in a regular culture, and as a result, there's lots and lots of people searching for certain words. Something became less popular, and less people are searching. The environment's changing as we speak all the time. But this is going to come back. You might want to keep this in mind as one of the advantages of learning, but we'll come back to this. So as I promised, the first thing I want to talk about is where did learning come, or how did learning relate to games, and what do I even mean by learning? And to do that, I actually want to go to the opposite end, and rather than thinking of traffic routing and advertisement, which are really the prototypical games that we're playing over and over again, I want to use very simplistic, silly examples. So here is sort of the classical two-person games that hopefully you've also seen. This is a simple coordination game in which, and this is maybe a standard game theory notation, there are two players here as a column player who is choosing between, row player, who's choosing between these two rows, and a column player who's choosing between these two columns. Their strategies are called A and B, and they both would like to coordinate, that is, play the same strategy. If they do coordinate, they get a payoff or utility of 1 each, and if they miscoordinate, one of them chooses A, the other one B, then they get utility of 0. That's a game called a coordination game. The Nash equilibrium of the game is, Nash equilibrium is any stable strategy where they're both happy with what they're doing. And there are a couple of them in this game. They can do both A, certainly that makes them happy, or they can do both B. Or maybe more disturbingly, they can run what's called mixed strategies. They're flipping a coin in the beginning with probability 50-50 of the two strategies, and that's a Nash equilibrium also. Picking on Dick for some reason, if he's playing a 50-50 mixing, then, I could also play a 50-50 mixing. So indeed, 50-50 mixing is as good as it gets, given that the opponent's mixing. This is not as good an equilibrium from our social welfare point of view or any player's point of view, because probably the 50% they're miscoordinating. But yet it's a Nash equilibrium. So these are the 3 Nash equilibrium of this game. Another game equally well-known and famous sometimes only has mixed equilibria, and that would be Matching Pennies. Here there are two players. The green player would like to match. They're choosing between heads and tails. The green player would like to match. The red player would like to mismatch, and the payoffs are 1 if the right thing happened and -1 if it didn't. And the unique equilibrium here is a 50-50 mixing. This is a game, so-called zero-sum game. The opposite interest, if I win, my opponent loses. Those games will play a special role in what's coming. Okay, so these are my two sample games. Now, why learning, and what do I mean by learning? So the classical solution concept, or classical outcome in games, has been Nash equilibrium, and I guess the famous theorem here is that Nash equilibrium does exist. As we have seen just a second ago, sometimes it has to be mixed strategy, that is randomized strategies, but it does exist. It's guaranteed to exist. This is not what Nash proved. The question that the originals of thinking about learning in game was motivated by is, how do the players know to find it? Can rational players find the Nash equilibrium? And there are many reasons this is questionable, or this is an issue. So if I go back to the classical reasons, then things like, remember the coordination game? It had 3 Nash equilibria. So the classical answer to how players find the Nash is introspection. They think hard, and then they know to coordinate on Nash. But no matter how hard I thought, how did I know to think of the same Nash as my opponent? That's a little problematic. There is also other reasons that is equally problematic, especially in large games. The players don't always fully know who they're playing against and what exactly the game is. And how are you going to find the Nash when you don't actually know what the game is? Introspection needs full knowledge of everything. That seems a little problematic, too. And then, because we're computer scientists, we also pondered that it might be computationally hard to find the Nash equilibrium. And indeed, Daskalakis, Goldberg, and Papadimitriou proved that it's PPAD hard. This was the first of these results. There is a sequence of other hardness results that even when a Nash is unique, even when otherwise life is good, finding it is computationally hard. And that's another convincing reason they won't be able to find it. So the first way that people started to think about learning in games is a way to try to find the Nash. Maybe learning is a way to find the Nash. So what do I mean by learning? So remember, we thought about it as a repeated game. So here is a game. You play over and over again. I'm going to denote this A is the action that a particular player can take. So AI is action of player I. And this happened in period 1 and then period 2, and they play over and over again. And I'm going to assume that the way we think about it, the exact same game is played at every period against exact same opponents, and people are looking for good average performance. Or they just learning to play this game. And the idea is that in the beginning, they don't know what's going on, but if they played enough, hopefully learning will help them. And they figure out what is the right thing to do. So that's what we're trying to model. So again, the first motivation for this is a way to find the equilibrium. And this was suggested or introduced by Robinson in 1951, who also introduced the one particular method of doing this, or trying to do this, called fictitious play, where the word fictitious play actually is a different view of a repeated game. There is no, in Robinson's mind or his motivation, there wasn't actually anything getting repeated. It's a sort of pre-play or chip talk on which you're learning how to do this before the real game happens. So when an important game happens, such as say spectrum auction as an important big stake game, there are indeed sort of pre-runs in which people can train to learn the game. And instead of this whole picture I showed you here as not the real game, this is the pre-play in which they're learning how to do this. And so the whole goal of this is just learning. That's why the name fictitious play. And here is what fictitious play concretely suggests you do is pretend in your mind or believe for a second that your opponent already knows how to play and is doing a randomized strategy. And what you're getting is samples from his randomized strategy. So given that if your belief were to be correct, and you were indeed doing samples from his randomized strategy, then it would be rational to best respond to the observed statistical behavior of the opponent, and that's what fictitious play is. So fictitious play best responds to the past history of the other player. So assumes that the statistically how often he played what strategy is the distribution, and you just best respond to that. And you think of this as a pre-play, as a way to learn the game. Now, what is Robinson hoping for? Robinson was hoping for that this leads to Nash equilibrium. And I will think about a little bit of what does it mean to lead to Nash equilibrium. So one way things could lead to Nash equilibrium is this. So for a while they do something, I don't know, and after a while they found the Nash equilibrium and they repeat it over and over again. If this happens, it surely led to Nash equilibrium. If you see this pattern in fictitious play, that is, if ever the case that a certain vector of behavior repeats over and over again, that clearly is Nash equilibrium. Okay, why is it Nash equilibrium? Because everyone is repeatedly thinks that he's best responding to statistical observation of the other players. In fact, it is what's called a pure strategy or deterministic Nash equilibrium. After a while, the whole history doesn't matter, and the only thing that matters is that last thing that they've been doing over and over again, and that's being stable here. So that's a Nash equilibrium. So here is a notation I'm going to use for this. It's a Nash equilibrium. I'm going to say UI, or utility of player I, is the value or payoff the player gets from this utility. This action A here is this thing they're repeating in green, and this is the player I's payoff or utility from this action. Here is what would be player I's utility for not playing this action, but instead playing this alternate action X. And if it's a Nash equilibrium, or it is a Nash equilibrium, if his utility is better than any other action he could do. And that ought to be the case here, because if it wasn't, then after a while, he would switch to X or something else. So that's the just explanation of the notation. And I'm going to refer to this as the no regret style assumption. No regret meaning player I does not regret not playing strategy X instead. He's feeling good about it. He's not regretting strategy X. Okay, so let me quickly try this out on my two promised simple games. So if you do matching pennies, and for some reason, to make life interesting or simple for me, I started one of the players off with a history that's longer than non-existent. So somehow the second player, that remember the one that doesn't want to match, starts with believing that he has seen the opponent play tails twice in a row. I'm not sure why. Starting from this history, what they're going to do is, I wrote down here in this line, the history they currently observe. So this player's Nash seen one head, 0 tails. And then this person sees one head, 2 tails, and what they respond to it. And what will happen in this sequence of plays, they're going to cycle around in a simple 4 cycle. That is, they started out playing head-heads. Apparently in this, they will do this twice. And then they're going to switch to playing this corner, do this twice. Then they're playing this corner, do this twice. Then they're playing this corner, do this twice, and so on forever. Can you just try that? This is what fictitious play does. So one funny thing about fictitious play, that's a deterministic play. If the opponent played heads 18 times and tails 17 times, 18 is bigger than 17, and you're going to be convinced to respond to the heads because there was one more frequently. And no matter how big 18 and 17 is, you keep doing this. That's what fictitious play says. And what they're going to do is deterministically cycle around. So one good news about this, that the distribution of how often they play each of the corner, each of the squares here, is actually the Nash equilibrium. Remember, the Nash was that they play 50-50 the two strategies, which means they land in the squares 1/4 of the time, and that's exactly what we did. The bad news is that we kind of cycled around. We didn't do a random distribution, we did a cycling, but the statistics are right, which is kind of interesting. Second, which is a bit more disturbing here, fictitious play on a coordination game. Here I actually added a little plus instead of the 1 to make the players favor one or the other in case they're neutral, to make it deterministic. And let's get them start with A, B. Remember this coordination game, they just wanted to do the same thing. But if they unfortunately miscoordinate in the beginning, something really horrendous happens in fictitious play. They miscoordinate forever from then on. After they miscoordinated once, they both going to switch. And then they both going to switch back, and then they both going to switch, and so on, forever and ever and ever. They never coordinate. Is there a good news here? I'm not so sure. Weirdly enough, this also converges. Like a play, I don't know if it converged, and certainly nothing very good. The payoff is horrendous. But these distributions converge. They're converging to 50-50. Right? They're playing one, 18 times, the other one 17 times. They're converging to a 50-50 distribution of the two playoffs. And as it turns out, whenever a two-person game converges in this sense, the distribution of play convergence, then that's a Nash equilibrium. What's more disturbing, they're not playing that Nash. Because yes, they're doing 50-50, but they do so in a coordinated way. In a coordinated way, that's horrendous, because it has really bad payoff. Even a mixed Nash, which is what they converge to, has a payoff of half each every step, and here they're getting 0. But it is the Nash equilibrium. So more generally, does this fictitious play lead to finding a Nash equilibrium? Usually not, but there are a couple of theorems that says that sometimes it does, one of which I just showed you an example of, being this one. Two-person zero-sum, actually, in a way, both of them are, what I showed you is an example for both of them. Two-person zero-sum games generally, and any generic 2x2 game, the two-person, two-strategy each game. They do converge, but only in this really weak sense. Like you see in a two-person game, it converged to the right thing, that it's a Nash equilibrium, but they're not getting the right payoff. They just statistically converge to it. And why they, so it converges in some sense, but it's a pretty weak sense. So maybe this isn't the right notion of learning. And I'm going to suggest that it isn't, and I will do this sort of twice. There are two different alternatives, which, if you parameterize them right, they turn out to be the exact same thing, which are more convincing versions of learning, at least have nicer consequences. So one version of more convincing is, what was wrong with this alternation of always miscoordinating is that they played deterministically. If they get convinced between 101 or 102, they think 102 is a little bit bigger, let's do that. I don't know if humans do this, but that caused miscoordination. So there is smooth fictitious play, which is trying to smooth this out. Let's not be so pushy about it. So here is one way to think about this. When we thought fictitious play using our notation, we were looking for to play next a strategy X. Strategy X that maximizes, that's the best strategy with hindsight. That is, given that the past actions were something a statistics came from, I take the action that would have been best in the past. Okay, they take the strategy X that if I look at what payoff I would have gotten given what the opponent played, this would be the best strategy. And this is a deterministic rule that deterministically chooses the best strategy. Well, assuming, unless there are ties. So here is a smoothed version. First of all, I'm looking for a probability distribution I would like to randomize. And instead of maximizing a strategy, I would want to maximize among probability distributions my expected payoff. Okay, I cheated. This didn't help at all. If you're maximizing the expected payoff with a strategy distribution, well, is going to pick a point mass distribution that picks the best strategy with hindsight. This didn't help at all. It's still deterministically picking the single best strategy with hindsight. But this way of writing it, one can help easily by adding a little term here. Let's please randomize whenever possible. So one way to do this is to add a little penalty function or additive function, or not penalty, a helping function with the entropy. When neutral, please also push up the entropy. So any little nu at least will make you randomize against equally good events, but if the nu isn't literally 0, then even similarly good event, you're trading off entropy against how good the response is. So you're adding a little penalty for, a little added term for entropy. You like to have a high entropy whenever possible, whenever it doesn't take with a big penalty of the utility. So this, for example, when you have seen, 99 copies of one behavior and 100 copies of the other behavior, that is, the two behaviors are barely distinguishable for you, then you're going to relatively evenly randomize because you're going to want to push up the entropy. The payoff is not so different. Here's another take that is different, or looks different, and was actually motivated from a different action. Actually, if I go back to the econ community's motivation, then they like to think of this as reinforcement learning. And reinforcement learning also said that let's randomize, because randomization is sort of a smoother thing. So if I have a whole bunch of things that happened in the past, I'm just think of myself as an experimenting person that's learning which strategy works, and sometimes this works, and sometimes that works. And here is something I could do. I'm going to maintain a weight function of how much I like strategies. Then choose strategies probabilistic with probabilities proportional to this weight. So higher weights means higher probability. And then do a reinforcement or an update function that reinforces the things that were good in the past. So here is one particular reinforcement function which goes under the name of multiplicative weight update or hedge, and originally due to Freud and Shapira, where you take above one a base of an exponential function and multiply it with how good the strategy would have been in the last period. Okay, so if you want to unravel this, then this WX has a bunch of these terms already in it. So what really is alpha to the sum of your experience is what you're getting as your weight. And you're maintaining these weights does exactly what we hoped it does. When the utility for a section is really good, you push up the probability. Utility is bad, I don't actually push down the probability, but implicitly I do because of the normalization term. So I push it up less, and therefore, at the end, normalized, I push it up more. Two theorems about these two learning method. First of all, and maybe very beautifully, these two algorithms are the same. Okay, so I had two algorithms, call them 2 and 2 prime. One of them was motivated by this reinforcement action that I'm experimenting, and I like to do more the things that worked well in the past. And the other one was a smoothed version of fictitious play. When I'm indifferent, let's randomize a bit. And it turns out that with the particular version I showed you, these two are actually the exact same thing, not hard to show. And second, that they both of them offer you a form of no regret guarantee. And that's why I really like them, in addition to being the same, which is already nice. So what do I mean by a no regret guarantee? But the guarantee is that for any fixed action X with hindsight, if I look at how much utility this player I got out of this is the utility he got over time. And this down here is the utility he would have gotten had he played X all the time. This is how much he would, with hindsight, like to have played X. It's reasonable to call that term that I have to plant in here to make it true, regret. That's how much he's regretting X. And remember, we were hoping for no regret. That was the Nash equilibrium standard. But this algorithm's guarantee is relatively small regret. And what I mean here is that if you play for a period of time t, and say the payoffs are between 0 and 1, you can have as much regret as t maybe. That's what happened in the coordination game. The good outcome was value 1, each time, t over a time period of t, and when they played, they got value 0. So they're regretting it very, very badly, as much as t. But what these algorithms guarantee is that the regret goes less fast than t, and in particular at the root t rate only. So that's a really nice regret star property. And from however many minutes I have left, I'm going to think of this. No regret playing as an outcome. So I'm going to think of what happens if everyone plays no regret learning.
So
yeah.
This small regret guarantee only works if all players use the same smoothness strategy.
No. This no regret guarantee is for an individual player, independent of what everyone else is doing. I guarantee this for myself, no matter what the rest of you are doing. I will, in a second, make the assumption that everyone is doing this, but I will not make the assumption that they're using the same parameters. In fact, I won't use the assumption that they're using this algorithm, and I want to point out in about 1 second that there are many other algorithms that achieve this, not just these two that are actually the same algorithm in different disguise. So I want to use, and I will spend a minute, a slide or two on this. I want to use no regret as a behavioral assumption. I do want to assume that people do something that have no regret. I do not mean to assume that they use this algorithm. They can do whatever they please as long as it has no regret. And in fact, there are many options of what they could do. There are many other algorithms. I also don't necessarily want to assume that it's root t is the amount of regret they're getting, as long as little o of t, that it doesn't grow as fast linearly with time. It's okay with us. Okay, so what happens if you do no regret learning? And maybe I was a little optimistic of how far I can get, so I need to skip some of the slides. You get to a distribution, which I'm going to, or Harton-Muscolel, following Harton-Muscolel, think of as correlated equilibrium, and I'll show you in a second why do I mean that. It has this no regret property, which is exactly what our learning guaranteed. We had a little bit of regret, but if I take the limit as time goes to infinity, then there's no regret. They correlated. They correlate on the X history. They're not an independent play. And this I best can show you in a different game. This is maybe also equally well known. It's a rock-paper-scissor game. Hopefully you all recognize rock-paper-scissor. And here's the cycle that rock beats scissor, scissor beats paper, and paper beats rock. It's also a zero-sum game. The following version of it, suggested by Shapley, is a little contorted rock, paper, scissor. Payoffs are over there. Same as rock, paper, scissor, except if you accidentally match, -9 each. It's not a zero-sum game anymore. So if you actually accidentally match, then 0 payoff, but then it's negative for both of us. The Nash equilibrium of this game is the same. But what happens in the learning dynamic? And I want to actually be generous and start out the learning dynamic on both players playing Nash. You just imagine both players are playing Nash, but randomization is tricky, as we all know. So maybe that player will play that strategy just a bit more often. He plays paper a bit more often. Then this guy's learning algorithm will discover that, hey, that opponent playing paper all the time or too much. The best response to that is better to play scissor. Indeed, he's going to play scissor more often. And then as a result, this other guy will say, oh, I see, he's playing scissor all the time. I better switch to rock because that beats it, and so on. And the dynamic will be this sort of spiraling at. And what they're really going to do at the end is some spiraling around the 6 squares over there. So it will be very similar to fictitious play, not very surprisingly, because this is really a variation on fictitious play. But every learning algorithm will do this, whether you do fictitious play or not. It avoids the diagonal, which is nice in the -9s. It does some sort of cycling, and it definitely correlates. It's not independent play. Okay, so this is what I call correlated equilibrium. So correlated equilibrium is a distribution of plays that you can correlate with your neighbor, but you should have no regret. Expected payoff is better than expected payoff for any fixed strategy with hindsight. This is exactly what learning converges to, whatever learning they do. If it happens to be independent player, then it's Nash equilibrium. It's a generalization of Nash equilibrium. Without this, Frieden and Shapiro proved a stronger version of the zero-sum game that we have seen already. We have seen from Miyashava that in zero-sum games, even fictitious play converges, but it converges in a very disturbing way without generating the right payoff. Here we get the right payoff. But we do get the correlated history. Even if I go back and have zeros on the diagonal as it was on rock, paper, scissor, I still get the same 6 cycle that people are cycling around. Okay, so I don't have so much time, so definitely want to talk a little bit about the outcomes, and actually the switch to one slide, I want to think of this as a model of learning behavior. So originally, as I said, learning came as a model of finding Nash equilibrium. From my personal perspective, this was not so successful. Most games, it doesn't do that. And given the hardness results, that's not very surprising. But then more recently, and more in the 90s, it sort of emerged that maybe it's a good model of human behavior or behavior. And there are a bunch of these papers. I picked some with some different themes. One of the earliest is Erev Ross, who's doing a 2-person coordination game experiments, and they're wondering which of the learning models matches better how people behave. But they're thinking it's one of those learning models. Then I actually was very impressed or liked this Fidenberg-Pejakovic paper from EC14, where they're actually explaining how lab experiments on a more complicated seller and buyer game are very, very well matched with a version of learning with a bit of recency bias, where you more heavily count on recent experiments more than past experience. And then more recently, in the current EC, Denis Nekipelov, Vasily Sirkanis, and I have looked at Bing adduction data and trying to match that to learning behavior. This is a even more complicated data set, and not a lab experiment, but actual data from auctions. So let me actually spend the last few minutes on quality of learning outcomes. And here is, I would like to step back and think about congestion games, because those are maybe the simplest where something nice can be said. So again, you think of congestion game as you're driving to work, and you're driving to work every morning, and every morning experience some traffic and might experience or change your path. When I think of congestion games, this is maybe a quick picture of what I mean by a model. Every edge has a congestion function, so with congestion x, it has this x over 100, or some other function of x is the delay on the edge. So in this particular very simple network, with 100 participants, splitting 50-50 is the optimal solution, but that's not a Nash equilibrium, because there is this alternate path here that has x over 100, that's a half, plus 0, plus a half. It's faster than the other path. And the unique Nash equilibrium is that everyone follows this alternate path. The trouble is they're all following these very congestible edges, and the total time went up. And this is an example that certainly Tim and I and many others have used a lot, called Brace paradox. And one of the papers that Dick referred to is this paper with Tim that showed something about quality of Nash equilibria, and this is one way to phrase it. And in this particular setting, and I won't page back to it, while the Nash equilibrium is not optimal, it's better than a centrally designed optimal solution that carries twice as much traffic. It's a sort of price of energy statement. It compares the Nash equilibrium to one solution to an optimal solution to a solution with a bit more traffic. And that it was motivated by what usually termed as the price of energy, the worst cost of Nash equilibrium compared to a social optimum. So if I want to think about learning, I have to take this, price of energy expression and put in something about average behavior in learning, and that has been suggested by a paper of Avram Blum and Mohammed and Katrina and Aaron. And here is the natural expression. We have a socially optimal solution, which is one thing, and then our average performance. Remember, I saw that average performance is average behavior, average cost, what I wanted to evaluate. And we'll think about if they, oops, I switched to cost because the congestion game is a cost game. Average cost over period of time t divided by the social optimum, and I take the limit as time goes to infinity. And that's referred to sometimes as the price of total energy because they're learners rather than finding Nash equilibrium. So in routing game with many players, I guess, and in fact in many, many other games, one thing that happened over the many years, and I won't have as much time as I hoped I would to tell you about this, is we maybe started by this Avram paper and then in a large way generalized and formalized by Tim Ravgarden's paper. We realized that many, if not almost all the results we have for price of energy extend to learning outcomes. That is, if people are learners, that's as good an assumption as if they found the Nash equilibrium. Now, in trying to optimize for a few minutes I have left, let me try to extract for you, in a way, what's the insight that causes this to be true without going into any of the details. So here is roughly what the proof technique looks like. You take the optimal solution. Remember, it's a repeated game, same players, same environment, so there is an optimal solution. And you tell them what is the optimal thing that they should do. What is this A star, the thing that the path they should drive on, or something, the route they should take. What's the optimal thing they should drive on? And then here is what no regret gives us. They're not regretting not having done that. In fact, it's good to point out they're not regretting anything. They don't have to know what the optimum is in order to not regret it. No regret guarantees that they're not regretting anything. In particular, you're not regretting the optimum, having not known the optimum. This is the one inequality we have in learning. We have, well, they're not regretting other things either, but those are hard to use in the proof. This is the one that seems very, very helpful. They're not regretting what we think they should have done. And what this framework really offers is a way to capitalize on this, and this is the technical details I'm going to now sweep under the rug, that this, in many, many games, and I'll show you quickly a list of what those games are, if you have this no regret property, that is, you're not regretting what you should have done in the optimum, that's good enough to prove that the solution is close to the optimal solution. So examples of this is Tim closed the smoothness framework, and things that we improved low price of energy in the smoothness framework include lots and lots of congestion games, so not just the one I had up first, but different cost classes of function. Lots and lots of auction games. You can sell items separately, first price, second price, all kinds of other ways. And even some other games down here that are not either. So lots and lots of games that have good price of energy. They usually have it for this reason. And all you need is people not to regret what they should have done in the optimum, and you're home. And the proof was actually so short it fit on the slide, even though I didn't go through it. So I guess one thing I definitely won't do is give you a single example of how you prove such a band, because I didn't even show you what the band was. But instead spend the last 1 or 2 minutes on a different advantage of learning, which we have been recently engaged in. So one thing I said in the beginning, and it's tempting to say, and I said that you might want to keep in mind till the end, is that learning has many other advantages, one of which it can adjust to a changing environment. But then when I tried to do any bounds, I didn't do this. So here is a game, repeatedly, same set of people here. And what we had is the stability assumption that currently mostly is in the literature is stable in the sense that these players here and the incentives are completely stable and fixed. And even though I didn't go through the proofs, I told you why that was. Namely, I need to know that there's a single optimum strategy, A star, and I need to use the fact that they don't regret this. Okay, if I have different people here in every step, then there wouldn't be a single optimal strategy, and maybe then it would be, you know, like we needed that. We needed that there's a single optimal strategy that they're trading off. So I guess I'm claiming that learning can adapt to a changing environment, and learners are better than this. And I guess in not, oops, actually I might come back to this, but what I want to at least tell you a teeny bit about is a very recent paper by Vasily Sirkanis and Todoris Likaris. Todoris is here someplace over there, and Vasily will be here in a week. Vasily is at Microsoft, Todoris is at Cornell, and both of them were Cornell students, where we extend this to a more general class of games where you can change the population. Our particular model assumes that the players might leave. So one way the population can change, and that's actually, I think, an okay model for traffic routing games, is that the origin-destination pairs of people sometimes change. You know, maybe this guy moved away and some other guy moved in the neighborhood, and that guy drives someplace else. So in particular, our model is that every player with some probability P leaves and then replaced by a worst-case other player. So this is a mix between slow change, because people are leaving with small probability, so the traffic today is probably pretty similar to the traffic yesterday. But in a way, worst-case shift, because the arriving players are completely worst-case and arbitrary, and in fact, the examples I slept through is one, maybe a simple example to show that in this kind of worst-case shift, you clearly have to try to adjust. Like here is a player, maybe he's around on those red periods. When he showed up, this was the traffic pattern. He found a good path to drive. But as life goes on, some of those people vanish and some other guys show up. And what I need from a learner is wake up to this fact. Please wake up to this fact and start driving up there. I'm going to actually skip the little bit of technical details that still were on my slides to not run over too much. But I guess as a high-level summary, I have to assume that I have to make an even stronger behavioral assumption that so-called people are adaptive learners, that they are capable of doing this. Like regular no-regret learning, there are plenty of adaptive learning algorithms in the literature. So if you want to be an adaptive learner, it's easy to do so. There are many in the literature that helps you do that. They're very simple algorithms, very similar to the algorithms that are regular no-regret learnings. Basically, let's be recency biased. What's wrong here is the past experience with that top road congested that's not relevant anymore. So let's be a little recency biased with your learning, and that should help. And as a result, we have some theorems here that I'm going to skip and maybe go to the, oops, mistake. How do I go back? Here you go. I want to spend a minute on sort of telling you what I hope you took away from my talk. So I want to think of learning in games as a good model of behavior. I'm both happy to recommend it as a model of this kind of behavior if you were someone who wants my advice of how you should play in games. Sure, if you have a lot of knowledge, it's good to start with thinking through what might be good in the game. But in games that do repeated, learning behavior offers all kinds of advantages. It's a good way to adjust to a changing environment. You do not need to know what the game is or exactly who you're playing against. And maybe this last point is something I didn't emphasize in the beginning. If it turns out your opponent's not very good at this, you can take advantage of him. This is in case of opposite interest. Like, if you play Nash Equilibrium, it doesn't matter whether your opponent's any good. you're getting the Nash equilibrium. But if your opponent plays badly, shouldn't I win more? And learning does that. If your opponent plays badly, I'm going to win more because learning helps me win more. And then what I more told you about, or I guess I didn't tell you as much as I hoped, but I more think about, is that learning players do well in games. That is, it inherits most of the price of energy results, and it even does so in dynamic environments. That is, learning can adjust to changing environments, and the play will guarantee, not every time period, but overall on average, high social welfare if everyone, or in fact most players, are adaptive learners. And I'm going to stop here and thank you. Oh.
Could you tell us about evidence that this behavior actually happens in practice? Discuss maybe some of the references you have.
Yeah. So I guess starting with what's easiest for me is my own paper. I hope in a new version, this is a work in progress. So we're looking at Bing data. Where previous analysis of this sort of adduction data was assuming that the play is at Nash equilibrium. One trickiness in advertising data that you don't actually know what people's values are because they don't tell us. So you have to infer their values, and that is usually based on the assumption that it's Nash equilibrium. There are two things I can tell you about the data, and I don't have pictures to show on like I do, but not on these slides. If you look at what the time series of how people are bidding in that data, it does very much looks like variation on fictitious play. They're going up for a while and then down for a while. It's more like a gradient descent of some sort. They're optimizing some objective function by pushing it a bit in a direction. Most people's behavior looks like that. Some people are stable, other people go up and down and trying to adjust sort of the way fictitious play would, going a little bit in some direction, or gradient descent. Maybe that's a better way to put it. Second, we definitely know that they have regret. This I know for sure. I don't know their value, but I know that there's no value under which they don't have regret. I know that. Therefore, they have regret. I don't know how much. That depends on what their value really was. But I know for sure they have regret because there is no single value under which they wouldn't have regret. So it certainly says that Nash equilibrium is not a good assumption. They're not at Nash. Whether this particular learning behavior is a good assumption, I'm not sure. Looking at the other papers, actually the first one, I can try to page back there. That I quoted they're trying to trade off which of the learning, whether fictitious play or reinforcement learning is a better model of behavior. So one interesting question there is that I don't know if we humans like randomizing. We probably do not. So both of these algorithms are doing randomization, and we agreed that that pure fictitious play, which is deterministic, is not a good model. I don't think two people would alternate miscoordinating 18 million times in a row. That's not very likely. So I don't know quite how to the way they want to deal with this, they, instead of running a one person against another person repeated play, those experiments did repeated two-person play in a large population. So say in a room, I don't know if it's as big as this, but say 30 people, and I randomly paired them, or maybe even more, 50, as many as say you guys, randomly pair them and repeatedly pay. Now from your perspective, you're learning, maybe learning, and you're doing repeated game, but you're not playing against the same opponent. In that setup, it seemed like every model of learning matches the data better than a Nash equilibrium assumption, and that most of the paper is about whether this model is better than that model. And certainly, it's unclear. These different models have different number of free parameters, and I don't know if they did a proper A/B testing to figure out if what they're doing in matching the data is simply a fact of how much you can fit the data, or what exactly happens. If I go to the third paper I listed, which is a Drew Friedenberg paper, his main point was there definitely from a seller-buyer game perspective, it's a very simple game. The proper you offer a take it or leave it price to a buyer, and the buyer offers a take it or leave it price to a seller in the game. If you figure out the Nash equilibrium, it's supposed to offer a price of 3, and in the game, they repeat it often enough, and it's not going to come out as a price of 3. It's really a one-person game. The second person is an automat in that particular thing. There's one experimental subject, and there, the recency-biased learning is a very good model of what the price. They should pick 3, and they're coming to 5, and it seems like 5 is the recency. The focus of that paper is more the recency bias. If I do learning in that model without the recency bias, they should have learned that 3 is the proper bid. But they recency biased, and as a result, they're getting the wrong outcome.
Yes.
Yeah.
So you say that learning players tend to do well even in dynamic environments. But it seems to me that a clever adversary would be able to figure out your learning mechanism and try to exploit that against you. Is that something that happens usually, or that could happen in games?
It could happen in games. Actually, yeah, it's a great point. So the criticism. So I like learning as a model, and I like it even more if I don't name which learning method they use. I make it as an assumption on the outcome of your behavior without naming the assumption on your behavior itself. And I guess one thing I'm thinking about is that maybe fictitious play is fine, actually, or variance on deterministic fictitious play, as long as the environment's random enough, that's good enough. But if I actually make the even stronger assumption that my named algorithm is what they do, so smooth fictitious play, then these algorithms lead into these cycles that I actually showed you of what they do. And then it doesn't take so much cleverness to figure out that there is the cycle, and you could take advantage of the cycle. You can beat me because you know I'm doing this cycle thing. And that's usually a criticism as a behavioral model of learning, that you would do this. Good point. Here is at the defense of what came at the end, so the good behavior. But you're offering me that some players do even better than no regret. It's possible to have negative regret. With no regret is a single strategy with hindsight. If I'm cycling and you want to beat me, you should cycle with me in the opposite way. You should not play a fixed strategy. That will give you negative regret. And you could do that, sure. As long as you at least have no regret with a single strategy with hindsight, the welfare guarantees stay. So I don't need people to be dumb. If they're smarter, sure, whatever. They will get negative regret because they do smarter things than what I assume they do. That doesn't change that the welfare guarantee stays. However, and maybe that's a good point to make, it's not safe to play a no-regret strategy because of this. Like, the welfare is safe. My welfare theorem or our welfare theorems are theorems. If everyone has no regret, some people are even smarter, they have very negative regret, welfare stayed. But it might not be good for the player, because you can shift the welfare towards you against me because I was dumb enough and played a simple algorithm, and you doing something smarter. Does that make sense?
Thank you again.